Good evening, respected participants. Welcome to day 4 of AICTE sponsored faculty development program on AI integrated next generation semiconductor devices. I trust these past 3 days have been intellectually stimulating with our distinguished resource persons sharing their valuable insights and expertise. Your enthusiastic participation and engaging discussions have truly enriched this FDP. Now, to introduce our distinguished resource person for the first session, Dr. Kavicharan Momaneni, I invite Dr. A. Chandrababu, the coordinator of the Subtle FDP. Over to you, Dr. Chandra, sir.
It's my pleasure to present to you the profile of today's resource person whose expertise will enrich our session. Dr. Kavicharan Mommanayani received B.Tech degree in Electronics and Communication Engineering Department from JNTU Hyderabad, M.Tech degree in Electronics Design and Technology from NIT Calicut, and PhD in VLSI domain from NIT Warangal. Currently working as an assistant professor at National Institute of Technology, Silchar. Prior to joining NIT Silchar, had a teaching experience of more than 5 years in various reputed institutions. He is acting as a program coordinator for M.Tech specialization microelectronics and VLSI design in ECE department, NIT Silchar. His research interests include microelectronic devices, VLSI interconnects, signal integrity, power integrity, device modeling, carbon nanotube interconnects, flexible electronic design. He is an IEEE senior member, has published more than 40 research papers in the domain of micro and nanoelectronic devices and circuits. Thank you for allowing me to introduce Dr. Kavicharan. Now, without further delay, I invite him to lead us into what promises to be an enlightening session. Thank you.
Thank you for inviting me for delivering a lecture in this FDP. Okay, good evening everyone. Okay, myself Dr. Kavicharan Momaneni, working as assistant professor in Department of ECE NIT Silchar. Today's my talk is based on the machine learning based modeling and optimization of VLSI interconnects and power distribution networks. Let me discuss about the importance of this ML based modeling for VLSI interconnects and for the power distribution networks. Okay, basically here we are using some artificial intelligence techniques to estimate the parameters like delay, power dissipation as accurate as compared to the simulation tools whatever we are using. The current simulation tools are taking more time for the, especially for the ASIC designs, especially for the full custom designs. Okay, we are going for the alternative methods like ML based methods to estimate performance parameters using these alternate methods like ML models. We are having enough simulation tools, but this is something like alternative tools for the interconnect modeling. Okay. That is the main motivation behind the ML modeling for the VLSI interconnects and power distribution networks. The organization of the talk is as given here, like I'll discuss about the role of simulation, importance of various devices and interconnects models, introduction to interconnects and the challenges of interconnects, various models, simulation results, and now then I'll go to the role of ML in interconnect modeling and some examples. Okay, simulation results and importance of signal integrity, power integrity. See, the basic role of simulation in IC design is regarding like when we design ICs, especially as compared to the breadboarding. For IC design, we must use simulation tools because in ICs and in processors, we will be having millions of components. Okay, to connect these components physically, it is not possible. Manually, it is not possible. That is the reason we use simulation tools, computer-aided simulation tools, and the corresponding layouts. Okay, that will be given for the fabrication units. Then the corresponding GDS file of the corresponding layout will be fabricated. Means initial days, older days, when there are components of like 10 to 15 components, 20 components, maybe 100 components, that can be done using breadboarding. Whereas to connect more number of components, more than 100 or 200 components, okay, Then the alternate approach is IC design. For that, we need simulation tools. We need CAD tools like Cadence, Synopsys, mentor graphics tools. Okay, and even simple CMOS inverter. If you take a CMOS inverter where PMOS and NMOS simple analysis like maybe ACR DC analysis by using hand calculation is impossible, because in CMOS inverter you will be having various junction capacitances, various resistance, and again at very high frequencies you must include the effect of inductance also. Then using those many RLC parasitics, okay, accurate calculation of this AC and DC analysis impossible by the hand calculation. Okay, that is the reason we must use simulation tools. And here the reason is here for accurate calculation of AC and DC analysis of this PMOS and NMOS. Okay, approximate analysis can be done using hand calculation, but whereas accurate analysis, for that the exact behavior of the device you must know. Okay, for that there is a clear role of the device models for the device models, and again interconnect models also. And just now I have told you to simulate millions and billions of components, we must use simulation tools. And this is the importance of simulation. And now I'll discuss about the role of the device and interconnect models. Okay, for any simulation tool, the heart of the simulation tool is a model. Okay, if model is accurate, then the corresponding simulation results will be matching with the post fabrication results. If model is inaccurate, then the whatever may be the optimization you do at the design level, if model is inaccurate and that is not describing the behavior of the corresponding device or interconnect under all possible conditions, then whatever the optimization you are doing at the circuit level, there is no use. The fundamental components is like a device model that must be accurate. If device model is accurate, then only there is a possibility of simulation results and post fabrication results matching. Otherwise, it is not possible to get accurate results as per the specifications given to you. And every circuit simulator, it should have built-in models for both device and interconnects. Okay, basically interconnects means here we call it as like to connect various devices, various circuits, various systems, we need interconnects. And there is a clear role of these interconnects at very high frequencies. It causes various parasitics, RLC components, and again it is leading to the various crosstalk effects, ringing effects. Okay, there is a great role of the discussion of the interconnects. Okay, and the quality of simulation is clearly decided based on the accuracy and computation time. These are the main performance parameters of a simulation: accuracy and computation time. If you want to simulate the ICR processor where it is having millions of components, okay, the computation time of the corresponding simulation takes couple of days also, because when we include all possible conditions, the simulation takes more time, especially for the testing and to test various corners, PVT variations, and again to test all possible input cases. Okay, the testing takes a couple of days also. Here we should discuss about the time to market. Time to market is a very important parameter, because companies they want to launch their product, maybe processor or IC, as soon as possible. Okay, for that the basic steps are like starting from the development of the new device models, and again corresponding device based models, and again after that that model has to be integrated into the circuit simulator, then circuit design, and again later they go for the layout. Okay, layout, after that they go for the fabrication of the corresponding processor. Okay, here time to market is a very important parameter, because if simulation is taking couple of days, and again after simulation, if you are unable to get the if you are unable to reach the specifications, the entire design has to be modified. Means here it's something like it's a repetitive process. Okay, that is the reason for any model device or interconnect model, in addition to the accuracy, computation time is a very important parameter. If you want to target higher accuracy means, then you must include all the parameters which decides the corresponding device or interconnect model under all possible conditions. And here there should be a compromise between accuracy and computation time also. The basic MOSFET model, like first order equation, we know in linear region and saturation region, ID equal to mu n C cos W by L into VGS minus VT whole square by 2. We are discussing about the accuracy and computation time. Okay, in every means even device and interconnect. Okay, if you want to target for the higher accuracy, you must include all the parameters. Whereas for the MOSFET first order equation, you are including only the parameters like mobility, oxide capacitance, and again VGS effect. But in addition to those parameters, various junction capacitance also must be included, and again at very high frequencies inductance effect also should be included. And when we are scaling down, then short channel effects will be dominant. Okay, that is the reason to get more accuracy of the corresponding device behavior. Okay, we must include all the parameters. When we include all the parameters, the computation time will be more. That is the reason with adequate number of parameters for the model, with that, then we try to get the lesser computation time. When especially for the full custom design, full custom design means where the designs starts from the scratch, means like development of new device, new material, and again new model, and the corresponding new device has to be integrated into the circuit simulator, and again circuit simulator, and again the entire fabrication process may be different. Okay, especially for full custom designs, there is a great demand for the new device and interconnect models, because for full custom design the specifications are very stringent. For that, there is a great need for development of new device and new interconnect models, and again those corresponding models has to be integrated into the simulator. And then there is sometimes what happened after starting from scratch like design means where we are not using any existing device models and interconnect models, and again we are developing from the new materials level, and again the new devices, and again integrating into the new simulation tool. After that, the layout, after making layout and after going for the new fabrication setup, if there is a deviation from the post fabrication results and the specifications, then there is no use of the corresponding full custom IC. That is the reason full custom designs takes more time, and again it is more costly effect also. And that is the reason people try to go for the semi-custom design, where the corresponding specification or processor or anything application that can be developed using the existing devices and existing device or interconnect models. Whereas if you want to go for the full custom means, then it takes more efforts also, and more money also, and more time also. And this is example like SPICE tool, we are having different models, level 1, level 2, like that. Okay. And till now I have discussed about the importance of device models and interconnect models, because for any simulation tool, these device models and interconnect models are the heart. Okay, if these are accurate, then there is a good chance of matching between the simulation results and the post fabrication results. And I told you just now, basically interconnect means it is a it is a basically wire used to connect components on a VLSI chip, and it is used to connect chips on a multi-chip module, and it is used to connect multi-chip modules on a system board. These are like various metal layers for joining different components. Okay, and basically the purpose of these interconnects are used to connect, used to supply clock, power supply, ground, and again control signal and data signals. These are mainly categorized into the three types: local, semi-global, and global also. Local interconnects means those are used to connect the transistors. Okay, whereas semi-global means those are used to connect various gates various gates and various small blocks. Okay, whereas global interconnects are there, they are used to connect power supply, they are used to connect clock routing and ground routing. Okay, because these global interconnects means the name itself tells you global means it is the corresponding wires are used to connect for the whole chip, because the power supply is needed by all the components, and some ground also we need, and clock, especially clock for the sequential blocks, we need clock supply also. Okay, whereas these wires are like different category are there, but these wires they run in different directions. Okay, to connect those different layers of wires, we need via connection. I told you every interconnect is having some parasitics. Okay, these are like resistance, inductance, and culprits. These are the culprits. These are the behind the undesirable effects in the VLS circuit design. These leads to the delay, power dissipation, crosstalk, ringing. I told you about the various models. Okay. We need accurate model. The basic model of the interconnect is like a simple wire. Okay, this was valid for the long channel devices, to connect long channel devices where device delay dominates the wire delay. For long channel device means for MOSFET, suppose MOSFET, if you take for long channel devices, device delay is dominating on the wire delay. Whereas if you go for the deep submicron designs, means after going for the scaling, then the long channel MOSFET becomes short channel MOSFET. Then in that, after doing this lot of scaling, then interconnect delay is dominating the device delay. Means you can observe here for long channel devices, the device the devices which are existing in the ICR processor, they are dominating the wide delay. Whereas if you go for the short channel MOSFETs, okay, the current MOSFETs, the interconnect delay is dominating the device delay. Any IC or any system, okay, we need devices to connect those devices. We need wires. Okay, the overall system consists of device and various devices, and again wires only. In current scenario of deep submicron designs, okay, the wire delay is dominating the device delay. Means overall devices are becoming faster, whereas wires are becoming slower. Our main target is to connect devices. We are using wires, okay, but wires are slower as compared to the devices. Then our target is to make wires faster. Okay, for that people are trying to go for the new materials. Okay, and new inventions they are doing. Okay, and some like optical interconnects or maybe some carbon nanotube interconnects. Okay, the different materials they are trying to use instead of using simple aluminum or copper wires. Okay, people are trying to go for innovative materials such that interconnect delay should be less as compared to the device delay. This is the basic structure of wires. Okay, basically these are like in orthogonal fashion. Okay, the bottom wire is in this fashion, and the other wire is in this fashion, red wire, and like this different wires. Means these are the wires, alternating layers run orthogonally. To avoid coupling, if they are running parallelly, there will be lot of coupling, capacity coupling between one layer to other layer. Means this is like a structure, like basically any processor, the structure is like a apartment level structure. Means the ground layer. Okay, ground layer, basically we use all components. Okay, like whereas our upper layers are used to connect the various blocks only, various components only. Means complete bottom layer is dedicated for the devices. Okay, on the other higher level layers and complete top layer, we use global wires to connect all the components. Currently there are around 12 to 13 metal layers people are using, metal wire layers people are using. These 1 to 12 layers are used to connect various components, various signals. Okay, whereas ultimately the top layer, here only we are using 3 layers only. That always the top layer is used for the connection of power supply, ground, and clock routing only. Whereas the complete ground layer is used to connect transistors, whereas the in-between layers are used to connect multiple blocks. These are called intermediate layers. They are used to connect multiple blocks, multiple gates. Okay. Whereas the top and bottom, there is a big difference. Is that global layers they occupy bigger area because basically here on top layer we try to use clock routing, power supply routing, and again ground routing. Whereas local interconnects which are used to connect transistors, they are very narrow. They are in very narrow because we are dealing with the nanometer MOSFETs. Okay, for that accordingly we scale down these local wires. The way we are scaling down the local wires, we are unable to scale down the global wires. Okay, because the global wire lengths especially we are unable to scale down because as compared to the older days, the current processors, every year we are trying to integrate more number of components. Okay, when we are trying to integrate more number of components to add more functionality, then we need lot of wiring we need. When more number of blocks are there in the processor as compared to 10 years back processor. Okay, we need lot of wiring, lot of power supply wiring is needed, lot of clock routing wiring is needed. That is the reason the global wire lengths are unable to scale down the way we are scaling down the lengths of the local interconnects. These are the main properties of interconnects: length, width, thickness, spacing, and this is pitch, aspect ratio, and electric constant. I told you this is the classification of interconnects depends upon the length. Global interconnects means more than 100 micrometer. Local interconnects means 10 micrometer. And this is the graph which tells that after scaling down, this is the x-axis about the process technology node, 130 nanometer, 90, 65, 45, 32 nanometer. Okay, y-axis is about the relative delay. The top one is describes about the global interconnects without repeaters. Basically, here we use repeaters. The repeaters are used to reduce the delay. Okay. Especially for the global interconnects, we use repeaters to reduce the delay. I told you just now, wires are in current deep submicron design. Wires are dominating the device delay. Okay, the entire system we are having devices and wires only. In the entire system, wires are slower, devices are faster. But we want to make entire system faster. For that, we try to have wires also faster. For that, we try to use we try to use repeaters, or otherwise we try to use some innovative interconnects. Okay, like maybe optical interconnects, or maybe CNT interconnects, or otherwise some flexible interconnects. Okay, and I told you just now this when we move into the deep submicron technologies like 250 nanometer, 180, 130, 90. The top one is the blue one. Global interconnects wire delays keep on increasing. This is the main bottleneck. Okay, as compared to the device delay, see the gate delay is nothing but the bottom one, thick blue one. The gate delay is decreasing with the technology. Okay, means gates are becoming faster when we move to the deep submicron nodes. Okay, whereas wires are becoming slower. Devices are becoming faster, wires are becoming slower. Even the local interconnects is nothing but the red line. Okay, these red lines are delays are comparable with the device delay, whereas the other wires, okay, the blue one where without repeaters the wire delay is too much high as compared to the local interconnects and the device delay. If we add repeaters, if you add repeaters, then this is about the global interconnects with repeaters. Okay. Then, where the device delays comparatively low as compared to the without repeater case. There is almost 2 to 3 order magnitude delay difference is there between the local interconnects and global interconnects. Always there is a great demand to reduce the global interconnect delay, where the devices are becoming faster, but interconnects are becoming slower. The entire system speed is limited due to the global interconnects only. That is the reason always there is a, when we calculate the worst case delay, the worst case delay is due to the interconnects only. These interconnects are limiting the system speed of any processor or any IC. That is the reason people's target is now, instead of moving towards increasing the speed of the device, they're trying to think about the increasing the speed of the wires only. And this is about the interconnect delay under different scaling rules. Okay, I told these are the main geometrical parameters like width, thickness, spacing, oxide thickness. Okay, length. Okay, here the main conclusion is here. When we go for the scaling, ideal scaling and constant thickness scaling. Okay, here local interconnects delays. Okay, this is about the local interconnect delay. The crux is for the short wires resistance. We take actually here for any parasitic wire. I told you there will be RC delay is there, RLC delay is there. RC delay, when we are considering RC delay, means inductance effect is ignored. At low frequencies only we can ignore the effect of inductance, whereas at higher frequencies we must include the effect of inductance effect also. For short wires, if we are taking RC delay, okay, for lower frequencies, your resistance is scales by 1 by S, whereas capacitance is scales by S. The entire RC delay is almost same, because here when we scale down the geometries, width is scaled by S parameter. Okay, where we are taking S equal to 0.7, width is scaled down by 0.7. Okay, and thickness also scaled down. Means almost all parameters we are scaling down. Then the overall RC delay is almost same, because R is scaled by 1 by S, C is scaled by S. Okay, RC delay is almost same for the local interconnects, whereas for longer interconnects, resistance is scales up actually 1 by S square, whereas capacitance remains same, and the overall RC delay is increases by 1 by S square. And the approximate the value is almost RC delay is increased by almost 2 order. For longer wires, and long wires means here global wires, okay, the RC delay is increasing by almost 2 times as compared to the local wires. Means when we are scaling down to deeper submicron technologies, longer wires are taking more time. Okay, longer wires are taking more time, means delay is more. Our target is to decrease the delay of these longer wires only. But unfortunately, we cannot. We are unable to scale down the global interconnect length, because each and every year we are adding more number of transistors, more number of components, and more number of blocks onto the IC. Okay, to connect more number of these blocks, we need lot of wiring for power supply, clock routing, ground routing. That is the reason longer wire scaling is we are unable to do. With technology scaling, gate delay decreases, whereas wire length increases, and again wire delay also increases. And this is about the aggressor and victim. And where the first case is like aggressor is trying to move from 1 to 0 and victim is at 1. Okay, and because of the inductive and capacitive coupling, the victim, it has to be at 1 volt, but the 1 volt level is decreased by same amount. This is called glitch. Whereas when aggressor and victim both are switching in opposite direction, then victim, instead of moving from 0 to 1 suddenly, there is a delay. This is called crosstalk induced delay. Okay, this is also due to the capacitive and inductive effects. Okay, means when two wires are running parallelly with some signal, okay, always there will be a capacitive effect and there will be inductive effect also. These effects cannot be removed, means we cannot make them zero. In presence of these capacitive effect and inductive effect and parasitic resistance, our signal should have the good signal integrity and again power integrity also. Means these in presence of these RLC components also, in presence of these glitches and noise also, we should have circuit should have good noise margin. Okay, when circuit is having good noise margin, then even the presence of these small glitches also, it cannot affect the output. That is the beauty of the digital signals as compared to the analog signals. Okay, these are the main challenges: delay uncertainty, overshoot uncertainty, crosstalk uncertainty, and power consumption, electromigration. Basically, electromigration means here when at a particular point of interconnect, at that point, if there is a high amount of current is flowing, there will be a current density. When there is a high current density at that at any point, then it leads to the migration of the molecules and atoms from the corresponding point. Okay, that migration of the atoms and molecules from the any interconnect point. Okay, that leads to opening or shorting of the wire. Okay, this is a permanent damage. Okay, when this is due to the movement of these particles only. When wire is open or short, then the corresponding processor blocks. Okay, they may not get the sufficient signal. Then it is a failure of the corresponding processor. This is the important thing. Okay, this here we have to discuss about the reliability issues. Okay, and these are the main challenges: power consumption and crosstalk uncertainty. Here, delay uncertainty, crosstalk uncertainty means here for any wire or any local or global wires where once we apply some signal, okay, after how much time, exactly after how much time the signal will be available, exactly we cannot estimate, especially when we discuss about the current deep submicron level designs. Okay, means always we try to develop some models. Okay, the model gives the approximate delay. The model gives the approximate crosstalk amount. Crosstalk means here how much amount of unwanted noise signal is induced into the neighboring wires. Okay, how much amount of noise is induced, that corresponding. None of the existing models are unable to predict the correct behavior. Means the main reason is these capacitive and inductive effects are especially capacitive effect is a short range effect, whereas the inductive effect is a long range effect. Okay, it's something like when there is a time varying current is flowing through the wire, there will be magnetic field around the wire. The magnetic field induces voltage into the neighboring wires. Okay, this magnetic field induces some voltage into the neighboring wires. Okay, this is called crosstalk noise. Actually, these noises no one can remove. Okay, our main intention is, we in presence of those crosstalk effects also, our circuit or system should work properly. That is our goal. Means signal integrity should be maintained in presence of these undesirable effects also. But our main intention is you try to estimate the crosstalk, or to avoid to nullify the effect of the crosstalk. Crosstalk will be there to nullify the effect of the crosstalk between two lines. If it is a critical wire, means we try to add some ground wires, or otherwise we try to add some shielding wires, or otherwise we try to increase the spacing between the wires. Okay, if you try to increase the spacing between the wires, then it is not a correct solution, because in processor, in wafer, okay, wafer is very costly. Okay, when we try to integrate more number of components, okay, hardly we give very less space for the wiring. Okay, and again, if you want to increase the spacing between the wire, then it is not a reliable solution, because our main intention is to integrate more number of components onto the wafer. Okay, that is the reason increasing spacing to reduce the crosstalk, or otherwise adding some extra ground wire. Okay, these are not the correct solutions. Okay, that is the reason, to avoid these overshoot or crosstalk problems. Okay, people try to innovate some new materials, or otherwise new signaling schemes people are using, such that less amount of noise will be there. And the main motivation of the any successful design of VLS circuit is to design and optimize the trade-off between these parameters only: performance, cost, reliability, and power. Okay. These things already I have discussed. Like we always try to go for the robust and reliable interconnect model, okay, which is critical for the success and function of every IC, sensor, and device. And for that, actually, for regarding here, packaging is important parameter. Okay, each device must be packed and electrically connected to the outside world. Okay, such that the external world dust particle, even single dust particle also can kill couple of transistors. That is the reason it must be packed even during the clean, even in clean room also they maintain such that there should not be any dust particle. And these are the major issues in interconnect delay. Okay, wires we generally we must place wires are placed very close to each other because there is no other option, because on wafer is very costly. We try to integrate wires and devices closer. But if closer means, if you are trying to keep more closer means, there will be more parasitic effects like coupling capacitance will be there, and again some mutual inductance will be there. And if you are trying to separate the distance, then these effects will be nullified. But always we try to go for the area efficient designs. Yeah. Always there is a trade-off. That is the reason we need some optimal geometry, optimal spacing of wires. And if we are placing wires very closer means, there will be large coupling capacitance, large mutual inductance will be there, and which leads to higher amount of crosstalk noise, and that leads to crosstalk induced delay. Okay, these are the multiple effects we will be having. And I told you, like, here there are multiple models are there, like simple short model, or otherwise simple capacitance model, RC model, RLC model. Okay, RLC with frequency dependent parameters, transmission line model. Okay, coupled transmission line model, full EM analysis of coupled elements. Okay, here when we keep on moving from the simple short model to the full EM analysis of the coupled elements. Okay, accuracy will be good, but it takes more computation time also. Here full EM analysis means we must use some numerical methods, finite difference time domain method, or otherwise finite element method. Okay, if you use those methods, okay, the accuracy will be good. But these FDTD works on some leapfrog algorithm method. Okay, where we to get the corresponding from to move from one step to other step to estimate the voltage and current parameters, it takes the input from the previous values. Means like that we keep on moves. Okay, here if you are using instead of simple capacitance, simple RC, simple RLC, if you are using some full EM analysis, okay, accuracy will be good, but at the same time it takes more computation time. I told you just now, for any model, device model or interconnect model, we have to compromise with the accuracy and computation time. If we need more accuracy means, then we have to compromise with the computation time. But for current designs of full custom design, okay, we need at the same time good accuracy, and at the same time the corresponding model has to be accurate. Okay, but whatever the cadence based models or synopsis based models, they are time consuming models actually. And this is the main target behind moving towards the ML based models. Okay, we have developed some ML based models. Okay, they are more accurate, they are good, they are having good accuracy as compared to the simulation tools. At the same time, the corresponding ML results are ML is taking very less computation time as compared to the simulation tools. Basically, the main problem is here how to assign a proper model. Problem is how to assign a proper model to each interconnect so that model predicts only the effects important for the system while preserving reasonable simulation time. This is the main important point. Okay, whatever the important effects we need, that has to be predicted. If you want to predict all the parameters means all the performance parameters, and it should be more accurate means, then it needs the model needs all the parameters. To run all the parameters, we need lot of computation time. Okay, always there is a compromise between the accuracy and computation time. These are the various existing models, Elmore model and Buckoglu and Sakura, like this. Okay, these are the various models. This is very old model, Elmore delay model. Okay, and here this is the fundamental equation of Elmore delay model. Okay, this is valid for only for the short interconnects only, and the model is purely based on the RC interconnects. Okay, where the delay is directly quadratically proportional to the length actually here. Another model here where RC delay means in case of RC delay Elmore RC delay increases with quadratically with its length. Okay, here we have observed that the insertion of buffer it reduces the delay proportional to its length. Instead of quadratically varies with the length, now the delay is proportional to its length. Observe the difference here. If we add repeaters in between the different points of wire, if we add a couple of buffers, okay, instead of increasing the wire delay quadratically, it will be varying linearly with the length. This is the big difference between the insertion of repeaters and with repeaters and without repeaters. Whereas here repeater size and inter-repeater separation that can be optimized to get the minimal delay. And another model is like RC delay model where they have estimated the crosstalk. And this is about another model, RLC model. Till now, whatever I have discussed, RC models where the delay estimation error is very high. Estimation error is very high, almost 100% error also there. Whereas if you include the effect of inductance, then the delay estimation error will be within the 15% only. And our main intention, our target is to get the delay estimation within the accuracy should be almost 99%. Means the model, whatever the mathematical model we develop, that has to give the results correctly with the simulation tools. Or otherwise, fabrication results. Okay, now we'll discuss about the simple structure, voltage mode, RLC interconnect, and these are the basic telegrapher's equations. Okay, the variation of voltage means here x and s. X is nothing but the position. S is our Laplace parameter. Okay. These are the variation of voltage and variation of current, which are purely based on the RLC components only. And the solution of this equation is written as exponential matrix. Okay, where phi is nothing but the 0 minus z minus y 0. Okay, these are impedance and admittance. Z is impedance, y is admittance. Z is impedance R plus SL, y is admittance SC, where L is length of the interconnect. Okay. Means here we have taken V of L comma S is nothing but the far end output voltage and far end current here is a function of your near end voltage and current. This equation, first equation is having some exact representation, and this is the frequency domain solution. And there are some models here. The function is in the form of some cos hyperbolic and sin hyperbolic, where z and y are nothing but R plus SL into SC. Okay. This is about the U transform, where we try to use some approximate function, okay, such that the transfer function, this is our transfer function output by input. Okay, here this will be simplified and such that we will be getting time domain function in a simpler fashion. Means we use this transform where the time domain function is represented as in the form of some poles. Okay, where here pi these are poles only. Okay, and these are the parameters, interconnect parameters, and power supply. This is VDD length typically we have taken 0.2 centimeter. These are the parasitic capacitance. Here, if you observe, these parasitic capacitance are nothing but per unit length parameters. And load capacitance we have varied, source resistance we have varied, and input ramp we have taken with some rise time of 0.1 nanoseconds. And these are the advantages. And these are the ramp response. Okay, ramp response of single wire, and these are the proposed model. Okay, here if you observe that there is a difference between input and output. Okay, that is called propagation delay. Propagation delay means the point where input touches the 50% of the peak, and the point where output touches the 50% of the point. The difference is called propagation delay. And this is about the previously I have discussed about the single wire. Now this is our H tree structure, where this is like a H-shaped structure where we are having multiple nodes. Okay, here the advantage of the H tree structure is clock source. When we apply clock source at the initial point, okay, at various nodes we will be getting the clock with the equal delay, same delay. And this is about the if we are having multiple wires. Okay, this is our mathematical analysis where we try to find out the crosstalk from one wire to other wire. Okay, when there are multiple lines, okay, these are the parasitic components, and these are the capacitive means, coupling capacitance are there. Okay, and mutual inductance are there, self inductance are there. Okay, from one wire means we have taken three wires. For three wires, there will be some capacitances and inductances parameters, and again these are the wire resistances, and we observe these are distributed parameters. These are not lumped parameters. At low frequencies only we can use lumped analysis, whereas for higher frequencies we must use distributed parameters. Means when frequency is higher as compared to the means the wavelengths. Okay, especially here we should talk about when the distributed analysis means where when we are having longer wires. Okay, when we are having long wires with wavelengths, means very low frequencies means when we have the higher time period and wavelength will be higher at larger wavelengths as compared to the as compared to the wide lengths, we can use lumped analysis. Whereas currently we are working with the very high frequencies, then wavelengths are very smaller. When wavelengths are very smaller comparable as compared to the intercurrent wide lengths, we must use distributed analysis. And this is about the noise crosstalk positive glitch simulation. When victim is grounded, instead of zero signal, we are getting some noise. This noise is due to the electrical and magnetic field coupling only. And these are about the till now we have used the copper interconnects. Copper interconnects, they are suffering from significant electromigration problem and higher resistivity that leads to higher RC delay. Overall delay will be more if we use copper interconnects, and they are having other hurdles like burnout time at current density of 80 megaAmpere per centimeter square. There is a burnout time of the copper, and even though they are, it is having some good advantages for the copper. Okay, but because of these problems, okay, burnout time and again higher delay and migration problem, electromigration problem. Okay, we go for the CNTs, carbon nanotubes. Okay, these are used for the fast digital switching, and this is nothing but the CNTs as interconnects. Okay, these are like different versions. Okay, graphene single wall nanotube, multi wall nanotube. Okay, and these are the possible replacements for the copper interconnect due to their large conductivity. If conductivity is large means then your resistance will be less, and they are faster also. Higher for higher switching applications we use these CNT interconnects, but these are allotropes of carbon with a cylindrical nanostructure, and these are the main properties of CNTs. They are having very low resistivity, higher conductivity, and they are having good current carrying capacity is there, and the temperature stability is very good, and almost 2800 degrees Celsius in vacuum and about 750 degrees Celsius in air. And these are one dimensional actually, and they are having large current means almost 1000 times more than copper. Means their burnout time is very high actually here. They're able to withstand even large current density almost 1000 times more than the copper, because the main problem is when we go for the high-end systems, supercomputers, where people are trying to work with the high amount of computing. For high amount of computing, we need lot of computations, means we need lot of power supply. For that, electromigration problems may occur for the copper wires, where the wires on the processor, okay, they may burn out. Means I told you just now, at any point, if current density is very high, okay, that leads to movement of molecules and atoms. Then that leads to opening and or shorting of the wire. That is the problem of the copper wire. Okay, that problem is solved using the CNT interconnects. That is the reason people are industry trying to move towards the CNT interconnects only, where the CNT interconnects are able to withstand even higher large current density, almost 1,000 times more as compared to copper. That is the reason CNTs are not having any electromigration problem. And this is the model of CNT interconnects, simple CNT interconnects. And these are the various parameters. And here also we use RLC modeling only. And now I'll discuss about the ML based physical VLSI physical design. And these are the main crux actually. Employing AA and ML algorithms in VLSI design and manufacturing reduces the time and effort. Especially time and effort means, I told you, when we try to integrate ML algorithms with the current existing tools, okay, they are able to work in a faster way. Okay, ML based tools are alternative to the current simulation tools in terms of good accuracy and very less computation time. And there is always trade-off between the selection of various ML algorithms and architectures with available training data and other model constraints. And this is the flow chart of the ML model. Okay, we here for ML means we need data set. Data set we are trying to get it from the HSpice netlist or maybe Cadence netlist. Okay, that data then we have to process the corresponding data. Okay, then, after that normalization we do, because normalize the input and response values means here some input parameters are like rise time. Suppose rise time we are taking, so I have taken rise time as 0.1 nanoseconds. Length I have taken some couple of millimeter. Millimeter means 10 power minus 3. Rise time is 10 power minus 9 in terms of 10 power minus 9. Voltage I have taken another input parameter, volts. Okay, different inputs with different ranges. Okay, that is the reason if you normalize all these input parameters, then it will be good. It will be, the model will be more effective actually. That is the reason we must normalize all the inputs such that the data will be in a proper format, and the data we have to separate into the training data and testing data, and we use some modeling, means we have to train the model. Then model evaluation we should do. And again, if we are getting desired accuracy means, then that is the final AI model. If the corresponding model is not able to predict that, maybe in device delay or maybe power dissipation, okay, or whatever the performance parameter you take, if it is not predicting means, then again you go back to the ML model, and again you just optimize the corresponding parameters, okay, till you get the good accuracy. And these are the several performance parameters like delay, power, crosstalk. Okay, different ML techniques we use. Our main intention is to reduce the computation time with good accuracy. And this is about the optimization. We use various surrogate models like ANN, SVM, GPR. Okay, and here data mining, ML builds a model based on the sample data called as a training data. Okay, and we try to get the predictions and decision without especially program actually. Means here data mining is also about the algorithms, but data will be explored through the unsupervised learning. Here we try to collect the data from the existing simulation tools. Okay, and and the corresponding data we use it to train the model. And we use one technique called clustering. Okay. Where the simple example I have taken where the transmission line is having multiple poles. Okay, we use some clustering technique. Okay, such that we try to find out the dominant pole. Okay, the dominant pole decides the performance. Okay, where the performance we try to compare with the exact performance, and always there will be some accuracy issue, but we try to compromise the accuracy and computation time. We use clustering technique. This is a simple example I have taken, like some fourth order system with -1, -2, -3, -4 other poles. Okay, that we are converting into the dominant pole cluster and next dominant pole to, cluster. Then it becomes second order system. Means the fourth order system we are trying to convert into the second order system, such that the fourth order system takes more time. This is a simple example, and we use pole clustering technique to reduce the order of the system. We use pole clustering technique to reduce the order of system, and numerator is reduced using the an approximation, Paddy approximation, where the complex functions, exponential functions will be uh, reduced into much simpler form actually. Means we use some ML based pole clustering technique and another approximation technique, such that the overall system transfer function will be simplified. Okay, and the results, the performance parameters, whatever we want, you will be getting with good accuracy. At the same time, the corresponding model results are computationally fast as compared to the cadence or HSpace synopsis results. And this is about the finding the cluster points actually, centroid. K-means algorithm we have used, and hierarchical clustering algorithm we have used. Okay. And this is the transfer function with generic higher order original system. Okay, this for numerator we are using Paddy approximation, for denominator pole clustering technique. Okay, and this is the algorithm. Numerator reduction. This is the algorithm. Okay, and this is a simple eighth order we have taken. These are the eight poles are there. That our main intention is to reduce it to the second order. For that, we found the first cluster is nothing but -1.06, and second cluster center of the second cluster is -5.13. The overall reduced denominator is, instead of eighth order, it is converted into the second order. Okay, where these are nothing but these cluster centers of first and second are nothing but the dominant poles basically. Okay, the dominant poles are trying to give the approximate behavior of the transfer function. Similarly, we use reduction for the numerator also. And I told you numerator reduction we have done using the Paddy approximation. Okay. And this is about the step response. Okay, there will be error, but the corresponding computations are much faster as compared to the simulation tools. These are the results using regression models. Okay. These are about the power dissipation and various delay plots using different functions. And next is about the signal integrity and power integrity. Signal integrity is nothing but the ability of system to transmit signals with minimal noise, distortion and noise. Whereas power integrity means we try to transmit the power with very much deviations. Means there should be constant power supply to the each and every block. That is our main target for the power integrity. Whereas poor power integrity and signal integrity leads to some distortion and timing errors, failures. Okay, our main intention is to develop ML techniques where we try to achieve good signal integrity and power integrity. And this is the proposed model. And these are about the ANN, and this is our data set. Okay, various geometries, and these are about the reflection coefficient, the transmission coefficient. and these are the errors. These are the various functions. Now ANN model for the power integrity, and we have developed initially we have developed database using the existing tools only. After that, we have trained our model. And next is about the CU-CNT interconnects. Means initially I have discussed about this copper interconnects. Now we have moved to CNT. Later we have moved to CU-CNT interconnects. Okay. And here the main problem is like, whereas in case of copper interconnects, propagation delay was more and electromigration problems are there, and at higher current density, burnout is happening for the copper interconnects. To avoid these problems, we have moved to CNT interconnects. Okay, but there are some problems. Okay, there are some drawbacks actually. Okay, of CNT interconnects. Okay, then we try to go for the CU CNT interconnects. Okay. Where we have done some optimal repeater. We try to find out the optimal repeater in session. Okay. Optimal, if you are using optimal number of repeaters for the global interconnects, okay, then your delay will be less. We have used PSO algorithm to find out the optimal number of repeaters such that delay will be less. Means for any system, okay, we try to have very less delay. Means for that, if you are using randomly selecting the random number of repeaters and at random locations, okay, that may not lead to the minimal delay. And this is the time delay of segment, and this is about the PSO algorithm. These are the results. Okay, and this is about the models. Okay, and next is about the single event transient. These are about the transient effect. Actually, means if there is any temporary and unintended disturbance or change in the behavior, okay, it's something like some electromagnetic pulse. Okay, it may be some radioactive particle if it is striking. Okay, how the behavior is there, means how the electron hole pairs will be generated, maybe in terms of device or interconnect. Okay, that analysis. And this, if there is a unintentional some electromagnetic pulse is there, that we have modeled as a signal. Okay, then we have found the analysis. And this is at various technologies, 21 nanometer, 14 nanometer technology. This work already still we are doing. And this is about the power distribution, power delivery network. I told you the main goal of the power PDN is to provide sufficient power lines to power the active device on the die. Okay, without power fluctuations. Actually, a lot of things are there, but I have another appointments also. Okay, so another meeting is there. I'll wind up. And this is about the another means domain, stretchable, flexible platform for mechanical and electrical collaborative design. So this is the stretchable interconnect block diagram, where for mechanical analysis we use HFSS, whereas for the electrical analysis we use cadence. Okay, means overall entire system we try to find out the delay crosstalk for the stretchable interconnects, where different bendings and different stretching angles. Okay, we try to find out the these device corresponding wire delay and ringing overshoot effects. We basically use these HFSS and Q3D simulators. And this is about the stretchable interconnect and corresponding transient response. Finally, this conclusion. Thank you. Any doubts? There is one announcement actually in our NIT Silchar. There is a PhD admission notification is there. 27th is the last date. If you are interested, you can apply. There are Group A and Group B. Means Group A means with GATE candidates they will get the stipend. Group B means part-time candidates. Okay, if they produce some sponsorship or maybe NOC from the corresponding working institution, they can join. They can enroll for the full-time and part-time. If you want to contact, you can contact us. My mail ID is available in the website and phone number also available. If you are interested to work in this domain, you can join with us.
Thank you, sir. Thank you, Dr. Kavicharan Mummaneni, for delivering such an insightful and comprehensive session. We deeply appreciate you taking time from your busy schedule to share your expertise with our FDP participants.
Okay, thank you very much, sir. Actually, my plan was to give tomorrow, actually.
We are very grateful, sir, for your session, and your contributions will certainly help our faculty members.
In our NIT, when inter-NIT tournament is there, I am one of the coordinator. I am getting continuous calls. When inauguration is going on, from tomorrow onwards, inter-NIT tournament is there.
Okay.
That is the reason quite busy actually today. Okay, thank you, sir. Thank you for inviting me.
Thank you. Thank you so much, sir, for attending.
Okay, sir. I am leaving, sir. Thank you.
Okay.
If you have any doubts, candidates, you can mail me also. Okay, fine. Thank you.